Hello and welcome to my channel Free Education to All. So today we'll be discussing about finite impulse response filter. So this is the introduction. Here we would like to learn what is an FIR filter and what are the advantages and limitations of FIR filter, what are the application areas of FIR filter. So here we would like to explore these things. So I hope all of us are having the basic idea of what is an LTI system. So let us brush up that concept first. So for an LTI system, consider this as an LTI system. So LTI system is having an impulse response, say h of n, and it is having an input x of n, output y of n. So the output y of n is related as x of n linear convolution h of n. So this is the basic relation of input and output for an LTI system, and FIR filter is nothing but an LTI system. So that means for FIR filter, this impulse response h of n is finite in nature. So that is why it is called a finite impulse response filter. Now if we look into the response y of n of an FIR filter, so we can write it as, say, y of n equal to b naught x of n plus b1 x of n minus 1 plus so on b n minus 1 x of, say, n minus capital N minus 1. So this can be further written as y of n, that is equal to summation over, say, k equal to 0 to n minus 1 h of k x of n minus k. So that is how it is related. Now this equation is what? This is the equation of convolution. That means this one and this one are exactly same thing. Now here we can say that this b naught, b1, these are nothing but the impulse response h of k. So we can equate that the coefficient, say, bn is nothing but the impulse response h of n for an FIR filter. So in that case we can write the transfer function of an FIR filter h of z as summation over n equal to 0 to n minus 1 h of n z to the power minus n. So this is the transfer function of the digital FIR filter, and it is of the degree of n minus 1. So now here if you observe, then you will find in this equation for the transfer function we do not have anything in the denominator. Denominator we have nothing. So what does it signify? That there are no poles. So we can say that FIR filters are all zero filters. So this is a great advantage of FIR filter. So if we have all zeros, that means it is always stable. FIR filters are always stable, because we know that zero contribute to the stability, whereas poles contribute to the instability. So all the poles need to be left hand side of the S plane or within the unit circle of the Z plane to have a stable system. So here we do not have any pole, we have only zeros. So that is why FIR filters are always the stable filters. Then another important thing is that FIR filters can be designed with exact linear phase. Now what is the importance, what is the application? The application is great in speech processing and that extended version as audio processing, video processing, augmented reality, virtual reality. So that is a huge application of a FIR filter because the linear phase response requires the precise, it meets the precise time alignment requirement of this kind of applications. If we come to the communication part for the data transmission applications, so linear phase prevents the pulse dispersion. Why? Because output is nothing but the delayed version of the input. So let us elaborate this thing. Suppose we have a FIR filter, okay, and we know the digital angular frequency ranges from -pi to +pi. So suppose this is the cutoff frequency, so this is omega c, this is minus omega c, so this is my frequency response of this signal. So this is h of e power j omega, so which is defined as h of e power j omega, that is equal to e to the power minus j omega alpha for this particular duration. So mod omega less than omega c and 0 for omega c greater pi. So when it is between omega c to pi, the response is 0, otherwise the response is e power minus j omega alpha. Now in previous slide that we have seen that output y of n of the filter is x of n convolution h of n. Now the Fourier transform version of it, e power y of e power j omega, that can be written as x of e power j omega convolution in time domain will result in multiplication in the frequency domain. So this is what we'll get. Now within minus omega c to plus omega c, within this particular range, the value of h of e power j omega, that is given as e to the power minus j omega alpha x of e power j omega. This is what we can write. Now if we take the inverse dTft, so what we get, y of n, that is equal to x of n minus alpha by applying the time shifting property of dTft. So this is very, very important. So output, what we are getting? Output we are getting as the delayed version of x of n only. So here filter is made for this purpose only. Within a particular frequency, the output will be same as that of input, and beyond that frequency output will get nothing. That is how filter is designed. So in FIR filter this thing is exactly followed, and here we are having the excellent phase response. So what we can observe from this equation is that linear phase filter does not alter the shape of the original signal. It simply translates the input signal with a delay of alpha. Now if phase response had not been linear, then we would have got the output signal as a distorted version of x of n. But filter is a device that is not meant for any attenuation or amplification. Its job is just to pass the input to the output within a frequency limit. So that can be achieved in a better way with the help of linear phase. So if we now summarize the advantages of FIR filter, then we find that FIR filters are always stable filters. These can be designed with exact linear phase, and these can be realized both in recursive and non-recursive structures. And FIR filters are free of limit cycle oscillations when implemented on a finite word length digital system. So this one is little critical. We may discuss these things in advanced part of digital signal processing. Now it comes with some limitations as well. Since it is a digital filter, it requires a lot of memory, and execution time are comparatively high. Now the implementation of narrow transition band, that means a higher length FIR filter, that design is complex as well as costly because it involves more arithmetic operation, and hence more adders are required, more multipliers and delay elements. So that is a limitation of FIR filter. So here we cannot have any length, very high length of FIR filter. So that is a restrictions, physical restriction. So these are the references I have used to prepare this lecture. You may also refer this for further studies. Thank you very much, and join me on part 2 discussion of FIR filter to find the zero locations of FIR filter. Thank you very much.